In this video, I want to start looking at some of the timing issues that I'm dealing with. I know I've got a couple of significant delays built into this circuit at this point, and they've been bugging me for some time. It's time to get those taken care of. Now, I know of at least one fault that I have that is going to require me to replace some ICs on the PCBs that I've already built, so I'll get to that when I get to it. But I also believe that because of the heterogeneous mix of series logic between LS and HC, some additional issues that need to be sorted out, and I want to take a look at those a little bit today as well. Now, I'm going to be honest with you, researching this timing stuff is not necessarily one of my strengths, and therefore this may take me a little bit of time. I am not sure if I'm going to get through all of this in one video. I really doubt it's going to be one. It might be two, depending on how things go. And it most certainly could turn into three or more. So this short series is going to be about addressing the specific timing concerns that I have on the circuit that's built already. Well, let's get into it. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. Okay, let's start on zeroing in on the two sections of this build that cause me a concern where I've added in large-scale delays into the circuit. The first is up here in this corner. Now this is related to control ROM 3, which controls the AND latch signals. And in that I have managed to delay the clock by 12 inverters between this IC and this IC. Now, if my memory serves me correctly, this happened over the course of two videos. Originally, I put this delay in, and then I found I needed to add an additional delay where I added this one. 12 inverters seems excessive. I can accept a delay of a pair of inverters, but not something of this magnitude. So I need to get to the bottom of that. The second section is now down here, which was added after all of this mess. And this is related to the reset circuitry to make sure that the AND latch of the first instruction after resetting happens after the program counter asserts onto address bus 1 what its intended value is, giving these two ROMs a chance to settle that address out and return the actual data. So the first place to start is up here in the corner. And I'm going to start by looking at data sheets. Okay, let's start by taking a good look at the 74LS193 IC that I started with. Now this is what I built my prototype on the breadboard with. Now I've pulled out the specs and printed them out because I want to be able to do some calculations off to the side. Unfortunately, I've got some math to do, so bear with me a little bit. But the specs here say that the LS193 should be able to operate at a maximum count frequency of 32 megahertz. Seems quite reasonable, actually. But I've been staring at this a little bit, and if I go back here, there's two things that drove me to have to put the delay in to begin with, and those were the propagation delay of upcounting through all four of the ICs and the propagation delay of downcounting or decrementing through all of the different ICs. So for example, if I went from 0 to -1, or from all zeros, all the bits being off, to all the bits being on, the propagation delay to get all the way up to the last IC was significant enough that I had to build in some delay there. Let's start by looking at what my build out actually looks like. And so if I was to lay this out, I've got four ICs here where I've got count up and count down, 4 inputs on each, 4 outputs on each, and then each are tied together such that if I am counting up, and let's just assume that the top line is up, and then I've got the carry to an up, and then carry to up, etc. As I'm up counting, if it carries, then it triggers an up count over here. And then if it carries, it triggers an up count over here. And then if it carries, it triggers an up count over here. And so that's the propagation across all 4 ICs. From the up count to the carry output is typically 18 nanoseconds. The down count to the borrow output is less than 18 nanoseconds. So this is 18 nanoseconds to get to that point, triggering the next IC. Now, if I take a look at up or down to any queue, that's 30 nanoseconds to get to that output. Now, what's interesting is that if this triggers an up count over here, it's really 30 nanoseconds here, which now becomes the relevant number because this 18 nanoseconds plus this 30 nanoseconds is my high water mark. These outputs are settled long before these outputs are. And again, if I work my way up, it's 18 nanoseconds here, another 30 nanoseconds here, another 18 nanoseconds here, and then another 30 nanoseconds here. All right, but what does that mean, Adam? Well, if I look at the longest path from the signal here to all the outputs stable over here, and I'm frankly not worried about this count output or borrow output on this most significant. I'm not doing anything with that. So my high water mark becomes this 18 nanoseconds, this 18 nanoseconds, this 18 nanoseconds, plus this 30 nanoseconds. Let me get a calculator out here. All right, looking at the calculator now. If I take 18 times 3 and then add to that another 30, that is a total propagation delay of 84 nanoseconds. All right. I convert that to seconds by dividing by 1 with 9 zeros after it. And then if I go 1 over that, I'm looking at 11.9 megahertz is the maximum frequency that I can handle, assuming that I don't need to do anything with the outputs here. Now, the other way of looking at that is that this 84 nanoseconds becomes the delay that I need to build in between the increment and the end latch. Now, if I look at the propagation delay of an inverter, which is what I'm using. So if I look at the propagation delay of a single 74LS04 inverter, it's going to be 9 or 10 nanoseconds, depending on whether or not it's propagating from low to high or high to low. Coming back here, let's divide that by 10, is 8.4 inverters, or 10 if I round up to the even numbers. So that, at least for the LS logic, tells me what I need to be looking at here. Now, let's go to my timing diagram. Now, if I narrow down here and look at the increment or load increment decrement, which happens on the falling edge of the clock, is when that's anticipated to take place, and compare that with the and latch, which is also happening at the falling edge of the clock, yeah, I need to build some sort of delay in there. It was right about here I realized that I have a fundamental problem with the way I have these signals laid out, and what I was trying to do was compensate for that. And of course I kind of had a sinking suspicion that that was the case, but I started rambling a little bit about different ways of handling this, not having thought everything through prior to hitting the record button. So you're going to hear me talk a little bit about some options. Ultimately, I have a decision to make on how I'm going to handle this, and likely it's going to be one of the options I lay out here. At this point, I'm almost wondering if it doesn't make sense to create a 4-cycle clock as opposed to a 2-cycle clock, meaning I have a 4-phase clock cycle where they're both low, one's high, they're both high, one's low. This 84 nanosecond delay in here between this signal and that signal is material. So I guess the question is, can I advance the latch piece of this so you can see that the rising edge of this signal is actually the business end of this? Can I shorten this to be a very small width pulse? And that's partly what I'm considering here. Is there any way that I can shorten that so that the increment happens well ahead of the and latch signal? That way I don't have to delay the and latch signal. I'm trying to think this through because this is material in the design of this CPU and its timing. All right, so let's say for a moment that I'm able to get the load increment and decrement to happen shortly after the rising edge of the clock, assuming that the bus is asserted in time. Ultimately, and there's that word I use again, I'll turn that into a drinking game. But if I look at that, and so here is my latch, here is my asserts, and at some point in here is my load increment decrement. I've drawn it offset, but perhaps that's in the middle of this clock cycle. Then the time difference between here and here has to be 84 nanoseconds for the LS logic. I want to be clear, I'm still thinking this through using LS logic. That effectively takes this 11.9 megahertz and divides it by 4, because now I've got 4 bits of the clock cycle. And that gives me my theoretical max CPU speed of 3 megahertz. Far from the 10 megahertz I was trying to get to. These are the ICs I've been using in my build so far. So these are Texas Instruments SN74HC193DR. Now DR, part of that indicates the packaging, and it means that they're on tape, and basically I just pull them out individually from here, turn around and solder them onto the board. Now, I also pulled the datasheet for these. And these are not quite as robust as I thought that they would be. So let's take a look here. Here is our propagation delay, or an up count to the carry out, a down count to the borrow out, or up or down to any Q. So given our diagram here, again, let's redo this analysis. Running at, and I'm going to pick on 4.5 volts. Running at 4.5 volts from the up count to its carry or down count to its borrow. That's 41 nanoseconds. And then up or down to any Q output, again, picking on 4.5, that's going to be 63. Now, again, this one is irrelevant, but this one is relevant up here, 63 nanoseconds. So at this point, if I take 41 times 3 and then add 63 nanoseconds, that changes that from 84 nanoseconds to 183 nanoseconds. Now, all the rest of this analysis still applies, but my maximum frequency here is 5 megahertz. Divide that by 4, I'm looking at maybe 1.3 megahertz as my fastest possible frequency. Well, that's not going to be good enough. Okay, so finally, since I'm at this point pretty much married to this up-down counter, I went out and I found the fastest I could possibly find, which is a Nexperia 74HC193D, and it's got comma 653 at the end of it. I'm not exactly sure what that means, but I got these from my supplier. These are on exactly the same type of tape as the Texas Instruments ones are, with the same pinout, same size. But I also grabbed its data sheet. Now, is this going to be the solution to all my problems? I honestly doubt it. But let's take a look at it. 74HC193, propagation delay. Count pulse up, or clock pulse up, clock pulse down to any output. So this is going to be this number right here. I'm going to take typical at 25 degrees, and that's going to be 23 nanoseconds. With, of course, this one being the significant one. At the same time, I've got clock pulse up to carry, clock pulse down to carry. These are both 14 nanoseconds, typical, and that's significant. So once again, looking at calculator, 14 times 3 plus 23 is a total of 65 nanoseconds, okay? If I convert that to a clock frequency that I can use, again, if I ignore the fact that I need to latch or anything like that, that's 15.3 megahertz. And again, if I divide that by 4, I'm at 3.8. Now, again, that's not quite the 10 that I was trying to get to. but it is significantly better than the 1.3 I would have been able to get with those slower ICs. Now you're asking, Adam, why didn't you just buy these to begin with? Well, the short answer to the question was I was trying to save $1, and I didn't actually read the data sheets to find out what I was buying. This is now, kind of an expensive endeavor because I'm now having to duplicate the purchase for these faster ICs in order to get the performance I'm looking for and eliminate some of this delay. Now, the reality is I could probably eliminate a good part of the delay with this, but I'm still hampered with roughly 1/3 the speed that I'm able to get with these than I would be able to get with these. So that's solution number 1 here to my timing problems. Solution number 2 is to look at this and see if I can pull the increment and decrement and load much closer to the rising edge of the clock, leaving all of this space in here for that resolution such that the unlatch happens at an appropriate time, allowing for that propagation delay. And again, the maximum amount of time I want to wait in here is 65 nanoseconds. That does effectively not necessarily a divide by 4 of this 15.3 megahertz, but closer to a divide by 2. Now, is that a divide by 2, divide by 2.5, divide by 3? I don't know. But a lot of it is dependent on how wide that needs to be. And I'm not worried about it for the increment and decrement because those are already taken care of. But the latch needs to happen at some point in time after all the asserts are taken care of, such that the data is stable on the bus before I try to do the parallel load. Now again, I can start to load at any point here, but I do have to bring that signal back low here at some point in time, which would indicate the actual latch point, allowing everything to settle out after that. Now, I'm kind of hampered by a decision I made early on, and that was to deconflict load and increment and decrement by having them all tied to the same signals going off to the register. If I had it to do over again, I would probably separate out the load from increment and decrement. That way I could have separate timings for each of those and not have to worry too much about it. But I've made my decision on that, and I've had the boards built and ordered, and I'm starting to assemble those, so I'm going to live within that constraint for now. But if I had it to do again, I would probably consider separating out the load from increment and decrement. So this is going to require a change to the control logic to implement, and I'm not exactly sure what I'm going to have to do with that. This is going to require me to desolder several of the existing ICs and replace them with these. And I want to start with the program counter first to make sure that I can whittle down that timing gap a little bit. I am not going to go all the way there with doing everything all at once because I am a fan of doing incremental changes. That way, if something goes south on me, it's only the last change I need to worry about correcting. Well, so what's next here? I'm going to take the night and sleep on it and try to figure out which of these two I'm going to tackle first. I guess I'll let you know when we come back. It'll be tomorrow for me, but it'll be right now for you. Okay, I've decided to start by replacing the counter ICs on the program counter. And the reason I made this decision is because I could go down the path of fiddling with the timing, but the problem is that once I replace these, I have to go back and fiddle with the timing anyway. Make sure that that's tuned. So rather than wasting time doing that first and then doing it again, I'm going to save the timing fiddling with the control logic to the very end. Okay, let's see here. Looks like I've got a marking here to indicate pin 1 that needs to go towards me. Okay, one thing I realized as I was performing the cleanup after completing the soldering is I had exposed a couple of copper traces. I'm not exactly sure if that's going to cause a problem or not, but it's certainly something I need to keep an eye out on as I'm going through and performing my testing. I may have accidentally bridged something without even knowing it. All right, now I need to clean it up and figure out how to test it. Okay. I've decided I'm going to use the code from video 61, which tests the R1 register functionality to complete this test. I've got them programmed on the EEPROMs here. Then I've got my board under test, which I want to put in here and move the R1 register or the program counter up here. Now, why did I choose to execute this as the R1 register rather than as the program counter? Well, I want a known good register for the program counter while I'm executing this test. And then the R1 register can be looked at thoroughly with that test that I wrote in video 61. I'll stick the code up here in the corner. And so now if I power on, this is the first time I've powered that on, everything seems to have reset properly. That, I believe, looks good. You'll have the benefit of seeing the code up there. I actually have to go looking for it. Load. There was a decrement, increment, 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 decrement, decrement, jump. So that appears to be working just fine. That puts these 4 counter ICs through their paces to make sure that all the functionality is accurate. I can increment, so let's switch this into the program counter position, which is where I really kind of want to have it homed while I do the rest of the work here. Okay, let's try that again and just go right into it. And again, that looks like it's working properly. Now, once again, I have not fiddled with the timing over here yet, or the timing down here yet. I have 2 more registers that have been built and tested that I need to upgrade to use the new counter ICs. Plus, while I was on vacation, I built 3 additional registers. Now, these have not been tested. But before I get into that, I may as well go ahead and replace those. So I've got 5 boards that I am going to upgrade to the new counter ICs. Well, I gotta be honest with you, I am not used to things working the first time, and while I could probably get used to it, it's not likely to happen. So I think this video is going to end up being shorter than I anticipated. I'm used to having about half my video occur after my first test on average. Anyway, I do still have 5 PCBs that I have to replace those ICs on. I'm going to do that off camera. I'll come back, and if I have anything to report during testing, I'll bring those up, and the next video will at least start with an update on those, if not some troubleshooting related to that. So beyond that, I need to look at the timing related to this control logic. And I need to look specifically at the increment, decrement, and load signals and see what it takes to bring those forward in the clock cycle and make that shorter. There may be some changes, pretty dramatic changes related to that. I have to get this timing sorted out in the control circuitry before I deal with this timing here in the reset circuitry. So time permitting, we'll start getting into this and start laying out a plan on how we're going to do it, and hopefully I'll get to making some changes here to the circuitry. We'll see you soon.